Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we're going to learn about searching and binary search. Specifically, what we're going to talk about is searching arrays and other linear data structures. So we're going to use an array for all of our examples in this lesson. However, later in the course, we'll learn how to search other data structures like linked lists, trees, graphs, and so on. So first, let's quickly define what we mean by searching. We're given this array, and it has integers as its items. Then we're given a target value that we want to find, so we search through the list to find this item. Here we want to find 30. It's in this third index, and the index is typically what you return as your solution. However, how you use this value will be defined by your problem. The most straightforward way to search is linear searching, and this is probably something that everyone is familiar with. It's naive and brute force, but it's always going to work. What you do is you walk through your array item by item until you find the element that you're looking for. Since it's possible you would need to touch every item, it's going to take O of n linear time. The upside to linear search is that it's always going to work. Regardless of how the array is constructed, you can always find an item using this method. So let's walk through that now. You start at the beginning, and we're looking for the target 8. We go 0, 1, 2, 3, 4, 5, 6, 7, and finally we find 8. So linear search is simple and naive and brute force, but it's very straightforward and easy to understand. A faster and more powerful searching option is binary search. What makes binary search so great is that it operates in log time, and it does this by taking the array and dividing it in half each time you make a move. However, binary search has one very strict constraint, and that is that the array must be sorted. Without a sorted array, you cannot use binary search. And one thing to note, if you see that your input is sorted in an interview question, you should always immediately start thinking, is this an opportunity that I can use binary search to solve this question? So we said that binary search requires your array to be sorted. The way it works is it first calculates the midpoint. Here, since we have 12 items, it's the 6th index, and since it's sorted, all the items to the left of the midpoint must be smaller, and all the items to the right must be larger. So we have 6 here, and then 0 through 5 come before it, and 7 through 12 come after it. So let's walk through exactly how binary search works. We have our input array, and we want to find the target 5. So to find the midpoint, we have our lower bound, which we'll call start, and our upper bound, which we call end. We find our midpoint to be 4, and here we didn't have an exact midpoint. It would actually be 4.5, which doesn't exist in the array, so we just rounded down. Then we compare our midpoint to the target. Our target of 5 is larger than the midpoint, so we know it must be in the right half of the array. So now we've eliminated this entire left half because we know the target value cannot exist there. So by eliminating this, we know 5 must exist somewhere in these remaining items. And now we perform the same process again. However, since we eliminated all the items to the left, we can now move our lower bound up to the first item that is still valid. So we create a new lower bound or a new starting point. Then we find the midpoint again between the start and the end. It's 7 in this case. We compare 7, the midpoint, to our target of 5. We see that 5 is less than 7, so this time we go left. So we eliminate the right half, or the half that goes from the midpoint to the upper bound, because we know it must be less than the current midpoint. So now we've seen after each move, we eliminate roughly half of the items and continue to create new bounds on our problem. This time, since we eliminated the right half, we can move our upper bound down. Our lower bound stays the same, since we know it must have been in the left half, and now we calculate the midpoint between the start and the end. Every time we make a move, we check if the midpoint is at the target, and this time it was. So when your midpoint reaches the target, you found the solution, and you can return that index. So let's just again walk through the steps of using binary search. You first find your lower and upper bound. Then you find the midpoint between those two items. Then you compare the target to the midpoint, and you can determine which half the target must be contained in, depending if it's larger or smaller than the midpoint value. Then whichever direction you move, and whichever half you eliminate, you can either move up the lower bound or down the upper bound. Because we're dividing the array in half each time, this is where we get that log n time. We just repeatedly divide by 2 over and over and over until we find that item. And that's why binary search is so fast. And now, we're going to implement binary search from scratch. We're going to implement this iteratively, but binary search also has a nice recursive solution as well. If you want to see that, it's in the article next to this video. We are also going to count the operations for our binary search, and we will compare those to a linear search solution. So let's dive in. We know we're going to be tracking the lower and upper bounds. This is how we find our midpoint in binary search, so let's initialize those now. Initially, our lower bound is just 0, or the first item, and the upper bound is the last item. To iterate through the array, we're not going to be going linearly, so we can't use a for loop. Instead, we'll use a while loop, and we iterate as long as our bounds haven't converged. So if the lower bound is less than or equal to the upper bound, we know we have additional items to still check. So the first thing we'll do is just increment our operations so we can track those. The key to performing binary search is finding that middle item, and we compare that to our target value. So first, we find the index of that item by taking the lower bounds index and the upper bounds index, adding them together and dividing by 2. This will find the index halfway between those. We also use math.floor to round down. If there are an even number of items remaining, the midpoint will actually be between two values. So when we add our lower bound and upper bound together and divide by 2, it could be a decimal. In this case, we round down to ensure that the index is an integer and valid. Then we just access the item at that index. First, we check if our midpoint item is equal to the target. If they are equal, that means we found what we're looking for and we can just return its index. If the midpoint item is smaller than the target, that means the target must be in the right half, so we need to move up our lower bound. So this eliminates the entire left half of all the remaining items. If the midpoint item is larger than the target, then this must mean the target is in the left half, so we need to move down our upper bound. When the target is larger than the midpoint, we know this means it must be to the right in the array. So we can move the lower bound up one index past the current midpoint, because we know the midpoint and below must be smaller. If the target is smaller than the current midpoint, it must be to the left in the array. So we can move the upper bound down one index below the current midpoint, because we know everything from the midpoint to the right must be larger. And this is all we need to continue to move our bounds inward, eliminating half the items, and then continuing to see if our midpoint item is equal to the target. If we finish the loop and the midpoint item is never equal to the target, then that means the item did not exist in the array. If that's the case, we're just going to return -1. So let's quickly walk through that. We start by initializing our lower bound and upper bound to 0 and the last item. We iterate as long as there are additional items in the array we haven't seen, and we know we're finished when the lower bound and upper bound have converged. Each iteration, we get the midpoint between the lower bound and upper bound, and then we compare that item to our target. If it's equal to the target, we found it and we return that index. If the target is larger, we move up the lower bound, and if it's smaller, we move down the upper bound. Now let's run some tests and compare it to linear search. Here we just have a simple linear search where we iterate through each item. If the item at the current index is equal to the target, we just return that item. If it's not, we return -1. We run our code, we search for the target 38, and binary search finds it in just 4 operations. On the other hand, linear search took 39. This is the exact reason why we love to use binary search when we can. Binary search is one of those topics that's best understood visually, so I'm going to share some additional resources that will really allow you to dig in and understand what's happening. There's links to this in the article, and I'll walk through them here as well. If you need some additional practice or just want to prove to yourself that binary search always converges on the target, I highly recommend going through these websites. Also, one other thing is I definitely recommend that you write out some arrays and solve them using binary search by hand. This exercise will really solidify your understanding of binary search and your understanding of how it finds that target. The first website I want to share is algorithmvisualizer.org. They have a ton of awesome algorithm visualizations, but specifically here, I'm going to walk you through binary search. So you can build it, and it will create random sorted arrays. Then you can hit play, and it will walk you to that target value using binary search. If you need a more detailed breakdown, you can step through it and see every single move it makes. Another great resource is the UCSF Computer Science Department. They have a visualization for both linear search and binary search. This one takes a little longer, so I'll let you go through it yourself, but I highly recommend checking out both of these sources. Thanks everyone, and I'll see you in the next lesson.